Okay, hello again. We left off last time looking at the convergence properties of the bisection method, and I want to return to that for one paragraph of the notes, and then we'll move on to the fixed point method for this lecture. Okay, so I'm just going to flip over to the board now, and Okay, so last time we established a convergence law, if you like, for bisection. And it was based on this idea that if we have the bracket we're working on, that the numerical solution will be the bisector there, and the maximum the error can be is when the root is at the far end, say, of one of those brackets. So you got that. So based on that, we derived this convergence law based on the maximum absolute value of the error. Remember, error is simply the numerical solution minus the true solution. So in this case, the value of the root when it's completely converged. And we got the fact that the absolute error basically halved each step. Now, this is useful to compare. I mentioned that this was a linear convergence rate. A general convergence law has the form that are, so say just look at the absolute value of error, it doesn't have to be the maximum value. It's the same idea. That the error n plus 1 is some constant a times e to the n to the power of q. And q is the order of convergence, right? So the error e to the n the q, and the key idea of this is why it's important, is the greater q is, the faster convergence is. So if we compare with this law for the maximum error, there's no power here, or there's a power of 1, shall we say. So this is linear convergence. In fact, this is this is a correspondence. So bisection has a q equals 1. It's linear convergence. Let me just start at the top of the board again, because this is quite an important idea. So we've got e to the n plus 1 equals a, so a is a constant, e to the n to q. Q is the order. So the greater q is, implies a faster rate of convergence. So this is a very useful way of comparing our different methods we're going to revisit. So in this module, we just revisit 3 and try and analyze them in detail. We're going to look at fixed point, and we're going to use Newton-Raphson as well. And we're going to try, but what we're trying to do each time is clarify what is Q. Okay, so the greater Q is, the faster convergence. So if Q equals 1, it's linear convergence. Q equals 2 is second order or quadratic convergence. You get the idea. If it was cubed, it converge even faster. This is a way of quantifying how quickly they are. So rather than just saying this method is quicker than the other, we can analyze them and say, well, we know that they are quicker than the other. Okay, so this is why I'm sort of laboring. Of course, we haven't said much about this constant A, which really goes before A. I mean, A has to be less than 1, right? Because the error has to decrease with time, whatever Q is, for convergence to happen in the first place. So for a bisection, A is simply half, yeah? Is the width halves each time. Of course, we're working in terms of maximum error, but the same principle harrows over. So that's the sort of thing we're looking at. We're looking at, first of all, whether the error converges to 0 at all, and then when it does, how fast does it? So this little formula encapsulates a lot about numerics. First of all, we want it to converge in the first place, otherwise it's no use to us. Secondly, we want to know how fast it converges, what the order of convergence is. Okay, so we know that bisection is linear now, and that's a good starting point to compare with other methods. Let me just go back to the to me. Okay, just to say we just done our first treatment of bisection method, and we found that it's linear convergence. Now we could go into detail with other methods. There's the secant method for bracketing, regular foci, all these methods. We're not trying to fill your head with lots of extra methods, but what we're trying to do is go into detail about a few of them to illustrate things, the principles of numerics, which are things like convergence and robustness of method. Okay. So with that I'm just going to now move on to the fixed point method. And let's use a few slides just to start you off, and then we'll go into more detail as we go forward. So these are taken from my notes. And what I need to do is get this. Okay. Let me tidy up things here a minute. Okay. So the fixed point method is still solving the problem f of x is 0. Okay. That's where the cursor is. So I'm looking at these slides where f of x intersects this x-axis. But the key idea with the fixed point iteration is to write it in fixed point form, and that means rewriting our problem f of x is 0 into a form that's g of x equals x. So f of x is our original function, if you like. G of x is what we're transforming to, and this is identical, hence the double-headed arrow here, to f of x. If you take x off either side, it's f of x is g of x minus x is 0. And we'll, in the tutorials, we're going to look at more examples of this to get you used to, because this rewriting process actually turns out to be the hardest bit of the fixed points. Well, one of the hardest bits. But the root has not changed. The method is we just moved the intersection point. So it's really helpful to have a diagram, and I may go onto the board and redraw this again, but let me just draw this now on this complete diagram. So you've got if you can understand this diagram in its entirety, you're starting to really understand fixed point method. So first of all, these crosses here, so these are in the lecture notes, these diagram. This is our original function f of x, and the root, of course, is where f of x is 0. It meets down this point here. What we've done is we've transformed it. We've got the same root, but we're now looking at a different problem, which is easier to solve for some cases, and that's why we rewrite it in this form as g of x equals x. So we're moving up to that point here. So this is our function g of x, and then this is x, and then we can apply our fixed point method to solving that. I'll come back to these ideas, and the idea is that once we can do it, we can then solve it using the fixed point method, and I'll talk about that. So let me now go back onto the board and talk a bit more in detail. Okay, so doesn't hurt to write out our definitions again. So the fixed point method is where we rewrite f of x equals 0 as g of x equals x, and once we've got that, then we can iterate. So these are just manipulating functions, the first line here. But then we iterate, so we take this function g and we simply do x of n plus 1 equals g of x of n. N equals 1 to how many times you need it. So once you have this function g for the problem you're thinking about, it's simply a case of repeatedly evaluating the function each time. So if g was cosine, for example, you just apply cosine each time. So just pressing the cosine number on your MATLAB or on your calculator repeatedly. So in a sense, it's very primitive, simple algorithm. It's just the stuff around it that takes a little bit of more understanding. So that's the key. That is the fixed point method. And but let me reiterate that diagram we did, and that by just drawing out on the board. Let me just draw like a nice big diagram now. A plot. We have our original function, and then call that f of x. And then that's our root there, you see. That's f of x is 0. What we've done is we transformed the problem. It's in cases where the function f is a bit of a pain to it's not a helpful function as it is. But actually, if we just take x off each side, you can get an easier function to use. So it actually constructs like this, and then we have the line. This is our line y equals x. Now I'm going to have to draw, because actually let me just let me use some color. Forget that I'm using a computer this year for this. So line y equals x then is this red line here. Okay. So, and then finally, if I get a blue line, say we have something like this. and this is our function g of x, and the intersection here, I can just extend down, and that's a fixed point, and then we call that our fixed point. So we're not still solving the root finding problem, we just rephrased it in terms of this function g of x, and then we can see if it converges or not. Okay, so we're going to carry on with this. We're going to give some more examples of fixed point method, and we're going to analyze its rate of convergence. Okay, so we've already got this result. Bisection is linear convergence. What is fixed point? Does it have this big A is less than 1 in that original formula that we looked at? Okay. Okay, so let's consider, let's go back to black. Consider f of x is cosine x minus x, which is 0, which is in fact the same example shown on the lecture notes there and sketched in my case. So g of x in this case is simply f of x plus x, yeah? Because f of x is g of x minus x. I've just rearranged that original formula, which equals cos x. So I've set this up to just be cosine, and that equals x. And then we iterate. We have xn plus 1 equals cos xn, which is also equal to g of x of n. So all we're doing now is then just repeatedly pressing the cosine button on our computer. And given the time, next time I'll go through a MATLAB example of this. Very simple MATLAB, so we can find the solution. And we iterate. And then beyond that, we want to look at the convergence properties of a fixed point. That's where we're going. So again, these should be familiar methods from last year, but hopefully we're going into more detail in order to really emphasize the principles of numerics, the principles of convergence, the principles of robustness, and that will carry forward into all the other methods we'll look at this year. Okay, so I'm going to stop there and I'll restart with some more fixed point and some more MATLAB next time.